I'm going to do two things in this lecture. The first half of the lecture is just going to be carrying on a review of very, very basic quantum mechanics, thinking about very things. And then in the second half of the lecture, we'll move on to the integer control. And I think it'll probably take the second half of this lecture and maybe the first half of Friday's lecture to just cover in some basic generality the integer quantum. So we're going to start in this lecture by discussing some simple quantum mechanics, and it's going to be the idea of a very phase. And I think this topic in quantum mechanics kind of captures the spirit of the quantum Hall effect better than anything else. It's really to do with the way quantum mechanics interplays with topology and geometry to capture a number of quite surprising consequences. And we're going to see the ideas that we learn here, we're just going to use over and over again when we think about integer quantum Hall effect, when we think about fractional quantum Hall effect. It's sort of the main idea that just keeps repeating throughout these lectures. So the basic idea is extremely simple. By the way, who's seen Berry phase as an undergraduate? Is it something which is generally taught? Who hasn't seen Berry phase? Okay. We don't do it in Cambridge. That's something we're missing, actually. So this is the idea. You consider a general Hamiltonian in quantum mechanics. And the Hamiltonian, we'll call it H, and it depends on two different kinds of variables, which I'm going to call XA and lambda I. You okay? Okay, so usually when you write down a Hamiltonian, you don't include the lambda i's. The XA's are the things that you usually include. These are the dynamical degrees of freedom in the game. Okay, so these are, if you're doing classical mechanics, these are the things you want to solve for. They're the positions of particles. If you want to do quantum mechanics, you have a wave function which depends on these XA's. Okay, so these are things that move and are not under your control. The lambdas are the parameters of the Hamiltonian. So they're not things you solve for. They're the things that you get to decide what values they take, because you have dials next to you if you're an experimenter, with flashing lights and things. You change those knobs and dials, and that's what determines it. Okay. So these are the dynamical degrees of freedom. And these are the parameters. And then we're going to play the following game. So you start by fixing the dials to be something specific, so the lambdas are something specific. And this Hamiltonian is going to have an energy spectrum, and you just place yourself in a particular state, an energy eigenstate. And I think it's, we don't lose any generality, we just say that's going to be the ground state. We can tell this story of any state, but let's just make it the ground state. So we place ourselves in the ground state. And we're going to take the ground state for simplicity to have energy equals 0. And what's more, we're going to keep this ground state to have energy equals 0 for all values of the parameters. Okay. It's because if the energy is not 0, there's always this dynamical phase, e to the minus I times energy times time, and we just sort of want to get rid of that because it's an annoyance in this. Okay, now what we do is the following. We go to our dials and we change our dials very slowly. Where slow means at a time scale that's small compared to the gap, sorry, a time scale that's long compared to the gap between the state you're in and the next excited state. Okay. So you vary these dials slowly, and what happens is the spectrum of the Hamiltonian is going to start to shift around. Okay. But there's a theorem in quantum mechanics called the adiabatic theorem, which says as long as you're suitably slow, if you place yourself in the ground state, you stick in that ground state as the spectrum shifts. There's a caveat. The caveat is that the ground state is not allowed to intersect with the first excited state. That's called level crossing. That's not allowed in this game. As long as you don't have level crossing, you just stick in that state. So you change lambda slowly.
So the system is gapped.
The system is gapped, and it's important the system is avoiding level crossing. Yeah, if you go through level crossing, so the first excited state comes down, when they separate again, there's no nice way to say which state you're going to. You're going to be in a superposition of the two, but in a complicated way that depends on all the details of the system.
In any case, the conditions, as you said, for adiabaticity is that it should be slow compared to
precisely. Okay, then finally we go back to the initial parameters. So we place our dials at exactly the same position as they were when we started. And the question we want to ask is, what is the state? So we started with a state which was the ground state, but we know by this adiabatic theorem that we cling to the ground state throughout. So we have to come back to the ground state, and the only thing you can change by is an overall phase. So the state we started in comes back to it with an overall phase. If this wasn't true, you'll also get this phase here, which was e to the I times energy times time, that's always ticking over. So we've set the energy of the ground state to be 0 precisely to isolate the part that doesn't come from that dynamic. Okay, so the slight surprise is that there is a contribution.
You set the energy to 0, for instance, by adding a constant to happen to it.
Exactly, yeah. I'll do an example after this, these generalities. So the slight surprise is that there is a phase that comes back, and it's a phase which depends only on very general properties of this Hamiltonian, and it's called the Berry phase. And it was discovered remarkably late. I think the first Berry paper is the early 1980s. Although, as Gautam said in the last lecture, there's been examples of this Berry phase appearing over and over again throughout the 20th century. And I think it was Berry who first realized this was a general phenomenon in quantum mechanics.
So this is some kind of a parallel transport or something?
It's exactly a parallel transport of this state, and we'll see that explicitly. Okay, so let's see how to compute it. So to compute it, gamma, we're just going to use the Schrödinger equation. Schrödinger equation. Of course, tells us how the state changes with time. The parameters, the Hamiltonian changes with time precisely because we're fiddling with the dials. So lambda changes with time. But because we've set the energy to 0, this just matches. This is true because we placed ourselves in the ground state. And so now we do the following. At every value of the parameters, so at every choice of those dials, we're going to pick a reference ground state with a very specific choice of phase. So we'll pick a reference state, n of lambda, with a specific phase.
Specific and arbitrary.
Right, so there's no canonical way to pick this, so you just have to make a choice. And we'll see shortly how different choices are going to affect it.
So this is like a choice of a section in the U1B.
Probably. Yeah. Okay, so the adiabatic theorem, which is what tells us that we stick within this class of ground states, says that the actual state that we sit in, as we vary, has to be equal to this reference state up to a phase. Okay, so this is just a
So n is the ground state at parameter value lambda, but
yes.
you choose some arbitrary phase.
With a specific choice of phase. Okay, and we'll just pick initial conditions such that in the lambda that we start with, So that's the lambda at time t equals 0. The specific choice of phase that we've picked coincides with the actual choice of phase of our state. Okay, so this is just the statement that u at t equals 0 is equal to 1. And now it's very simple. We just take this formula and we plug it into the Schrodinger. So what do we find? We find that psi dot u dot n plus u of n dot, which has to be 0, is u star u dot. U is just a phase, remember. It's the overlap of n with n dot. But we know how n changes with time, because it's only changing with time because we're playing around with these dials. So n's only changing with time because lambda changes with time. So we get far. So what sits here is important enough to give a name.
Can I ask you something that's
Please,
bugging me
yes.
a little? I'm sorry. You know, as we change these dials, our Hamiltonian, as you say, changes.
Yes.
Now it's okay to set the energy of the initial Hamiltonian to 0 by a choice.
Mhm.
But then once we change the dial a little bit, wouldn't the new Hamiltonian have
Typically, so I'm just going to define my Hamiltonian such that the ground state energy is 0 for all values of lambda, which I agree is artificial. And if you don't do it, you have to include in here the dynamical phase contribution, which is also there.
I see. No, I mean, then the arbitrary constant you would have to add would be time dependent,
Yes.
because as you change lambda, you're
Oh,
changing.
that's true. Yes.
So you're not keeping track of that.
Yeah, this is a very slick proof. It's sort of it's much shorter than most proofs in textbooks precisely because of these issues.
Okay. Yeah, probably after taking all that into account.
I mean, basically, your age of lambda
Yes.
is the original age of lambda minus E naught of lambda.
That's right.
If you like, yes. But my h was defined to have 0.
Yeah.
And if you do that shift, then your new Hamiltonian, of course, will have 0, energy at every E.
That's right. And this E naught of lambda part is exactly what's going to give you the dynamic effects. The e to the I times the integration over time of E0.
So you just have to keep that extra phase.
But that's not the phase we count.
Yeah, okay. Fair.
We'll actually see shortly the distinction between that phase and this phase. Okay, so we're going to define the Berry connection. Which I'm going to call with a curly A, because capital A is always going to be for electromagnetism. So the Berry connection is the overlap of the ground state with the variation of the ground state with respect to the parameters lambda and delta. Okay, then this equation here is easy to solve. U, remember, is a phase. This is the Berry connection. And so this equation here tells us that U of t is equal to the exponential lambda it's just solving this differential equation, which means that the total phase, e to the I gamma, is u of t after I've done a circle in parameter space. And so it's given by the following. This expression is saying that we can see the difference between the two phases. The dynamical phase obviously depends on how long you take to go around the ground. This phase doesn't care how long you took, as long as the adiabatic theorem was valid. But it does depend on the path that you took. So it only depends on the path, not the time. That's really the way to distinguish these two.
So the second line, the left-hand side of it, only inside two states, or is it just a
Sorry, which line am I looking at?
that particular?
This line?
Is it between N and N, or is it?
It's the overlap of
No,
N and
no, on the left-hand side. Is it of this kind, or is it just?
Oh, these are just numbers. Yeah, so NN is 1 by definition. N was yeah, so if you put NN on either side of this, these are just numbers, not operators. So it's the same thing as 1. Yeah, I took the overlap with N to get.
With side, then you overlap. You overlap with side.
The overlap with N.
But then you go
But that's equal to
This was 0.
We just solved the next one.
I guess the left-hand side is also some matrix, right? N.
And then you multiply by u.
No, but
U
is a phase, U is not an operator.
No,
Yes.
it's
It's a phase.
It's just a phase.
Just
It's a number. It's a number.
And if you overlap with n, you multiply by u star.
Yeah.
So that's name is overlap with psi. Psi was two times n.
That's true.
Yes.
But it's equal to 0. So either way. But U's are just numbers, they're not numbers.
Why is psi dot 0?
Because psi dot is, by the Schrödinger equation, is the energy of psi, and I set that. Alright, so this is the answer for the Berry phase, and it depends on the path. But not the time table. We can see explicitly the answer to your question. It's parallel transport, because that's what connections do. They parallel transport things. This is a U1 connection, so it's parallel transport.
So different choice of n will correspond to pure base transport.
Very good. Let's see. We made this arbitrary choice at the beginning of the phase for these reference states n. So suppose we picked a different phase. So suppose we picked a different different reference states. Well, these reference states were always the ground state, so the only thing I get to change is the phase of the ground state. But I'm quite at liberty to choose a different phase for every value of lambda. So I can choose a different set of reference states n prime, which are related to the n's by this. If I plug n prime into this definition of the Berry connection, I get a different Berry connection, which I call a prime. Which is precisely the same as the other Berry connection plus a gauge transformation. Okay, so it's exactly the same kind of gauge transformation we meet in electromagnetism, but now it's for this slightly more abstract connection. It's just like a gauge transformation.
Sorry, David, let me ask Ronald's question again.
Yeah.
As you're varying the parameters of Hamiltonian, your state is changing, right? So what does it mean that psi dot was 0?
There's some total derivative versus partial.
And otherwise, we have for
It's just setting it's just not keeping track of the energy you would get.
No, but forget about the energy. The direction in Hilbert space is changing.
That's true.
Sorry, what's the question?
There's a total derivative versus a partial derivative. One of these vanishes and one doesn't.
Yes,
That's what's going on. Which one?
Sorry, what's the question?
The psi itself is varying. Psi is a constant.
psi is changing.
Yeah. Because the parameters are changing.
But the equation that David wrote down was d by dt of psi was 0.
Partial derivative.
Partial derivative. Can you just go through the derivation again? I just want to see what we use.
Let me see. So this. This is the. This was the Schrödinger equation. This is the thing that vanished.
I think it's
No. What is Schrödinger partial there? I didn't understand.
Yeah, okay, this is what I'm not sure.
I think it means it doesn't. You don't account for the change in lambda.
No, I thought the change of the state period is the instantaneous, the rate of change
Yeah,
of the
that's
state.
right. That's right.
It's
It's
not
just
partial.
Yeah, that's right. It's just the change of it. That's right.
There's no caveat there, right? The rate of change of the state
That's-
is the instantaneous Hamiltonian times the state.
Yeah, because of the
And
irrevocability.
then the total change in the state you know how to compute because you say it's the ground state of the instantaneous Hamiltonian, right?
I think that's what you're
So you just use that. You put for psi the ground state of the instantaneous Hamiltonian and compute d psi over dt, the total time derivative.
It's just that.
But he used that the
No, the state
has not changed the infinite. There's some second order business.
It's just adiabaticity that
No,
you are
no, no.
slow enough, so this change of state is almost.
That won't give you the phase.
No, the state has changed, but it's the ground state of the
change
instantaneous
has-
Hamiltonian.
No, let's just go through David's derivation again.
Okay.
That the derivation was that psi naught was equal to 0, and therefore you got something.
Yes.
So where did that first
No,
statement
I
come?
think it's psi dot equals h.
Actually, that's why that came from that slickness of
That
subtracting.
thickness accounts for that.
That's
The what?
subtraction.
No, subtraction is only an issue of phase. It's you're changing direction in it. That,
No. Actually, the correct statement is that psi dot is h of psi, but psi is the
Yeah,
instantaneous
it's
ground
E naught,
state.
E
So
naught.
it is the instantaneous value of the energy.
So, but in particular, if you set your h to have e naught equals 0, are you saying psi dot is 0?
Yes, because
Can't be, because
actually it is it's the instantaneous energy. That if you get track of the instantaneous energy, he's just saying that I d psi dt is the instantaneous.
But then you would say that the ground state is not changing as you change the parameters, which is not true.
No, the ground state is changing. It's the instantaneous Hamiltonian ground state, which is different at every time.
No, but then what is the state inside? If we could just go through the derivation.
Yeah, let's
So the ground state is changing because h is changing as time
The
goes by.
keep the E naught, I think.
Hey, he's confused about next step.
See, uses
There is of course a next term in the adiabatic expansion.
Look, I just want to see how the derivation works.
So this is equal to u n dot plus u dot n.
dot.
Wait, the psi was equal to un, right?
Psi is equal to
So then d by dt of psi is not del by del. I mean, total derivative of
It's
psi.
total.
total derivative.
Total.
Is this?
And that's actually equal to some instantaneous energy times psi.
No, but if that was true,
Yes.
and that instantaneous energy was really 0, then you're concluding that d by dt of psi is 0.
No, it's not zero. It's not zero. The instantaneous energy is changing as the Hamiltonian changes. But he's not keeping track of that phase. He's not keeping track of that phase because that will give you a contribution that depends on time.
I thought he's changing his Hamiltonian to make sure that the instantaneous energy is 0. He's changing the 0 mode of the Hamiltonian.
No, that means he's constantly adding some constant.
If you just
with
added
time.
it to be
Yes.
not 0 but some e lambda times n.
No, he's constantly adding a constant with
I
lambda.
have a suggestion. I'm going to do a concrete calculation now. I'll do the concrete calculation and then we'll come back and we'll address these issues. Because Shiraz is right, the state is changing, and we'll see in the concrete.
But I mean, that is part of the slickness with which you set E naught to 0 actually is not true. There is a contribution there. But
let's
that's
see. Because this point is particularly very explicit.
Isn't it true that the directional change of psi in the vector space is due to lambda?
No arguing that.
So there is a lambda change and there is an instantaneous change. So there is a lambda change that takes you, on a path in the vector space. And okay,
Let's see.
I think the example.
Let's see the example. So the example is very simple. And it should be simple enough so we can actually figure out what's going on. So it's just a spin half particle. So it has two states, up and down. And it's a two-state Hilbert space. The Hamiltonian has to be a 2x2 matrix. And it's just going to be the Hamiltonian for a spin half particle in a magnetic field. So B is the direction of the magnetic field. Sigma is just the Pauli matrices. This has two eigenstates plus B and minus B. So I'm going to subtract from this, add to it B, which is the magnitude. So this was Sandeep's issue, that add explicitly to the Hamiltonian the E0.
Could I make a suggestion? Yeah. Let's consider the equation psi of t times psi of t is equal to 1. Psi of t. Psi of t. Now let's differ.
Exactly.
Psi of t is equal to 1. Now differentiate. To get psi times psi dot is equal to 0.
That's right. That's exactly.
Oh, but the other one. I suppose.
You can solve this, which is the derivation plus e to the I multiplied by
I think this will solve the.
How are you doing? Did you?
No, I mean, I think if you just kept that extra phase, everything is fine with Schrodinger and that's what at least we think.
But in this case, there is no extra phase. That's
Choose the ground state to have zero energy. You can do that.
What is lambda here?
B.
B. So as you change B, clearly your eigenstate of the instantaneous Hamiltonian will have a different energy, right? Now,
No.
in this case, I see. Okay, you rigged it up. All right.
So you always make it up.
Oh, so then it's fine.
But then the derivation will make sense.
Yeah.
Yeah, but then what is the psi dot being 0?
There's something wrong because psi dot is changing.
So let's see what happens here. There's two ground states. There's one ground state. When the spin is down, which now doesn't mean down in the z direction. It means
down in whatever
parallel to the direction of B. When parallel to the direction of B, you get ground state 0. Otherwise, ground state 2B. As long as B is never 0, the energies of the two states are different. So we're going to vary the direction of B. The spin is going to vary. As long as the magnetic field never becomes 0, you can apply these ideas. Okay, so how to do
it might be a case where because it's a rather special case where the change in the state is second order in the adiabatic approximation. So the adiabatic approximation is there are of course corrections which you systematically compute.
Yeah.
So this might be a case where it's second order. But the adiabatic approximation is not wrong as a systematic approximation.
No, nobody's questioning the adiabatic approximation, just questioning the derivation.
But the first term in the derivation is what David wrote down if he kept track of the change in energy, which for this case is 0.
Now, I put in the adiabatic approximation as something strict into the derivation.
You did, and the only term you didn't keep was the change due to the instantaneous energy, which in this example is 0.
But I'll always take examples where that's 0, so that you don't have to worry.
But let me just restate
what will happen if you don't put the plus mod B? I mean, the physics of
Then
the
just
very
become
same
the
doesn't
extra
change. You
dynamic
just get the extra.
Let me just restate what Sandeep said. You see, to get your phase, you're doing an integral over psi dot, but over an extremely long time.
Yeah.
So if psi dot was something non-zero, you in fact would have got an infinite phase. You'd have got an infinite change in your state because you're doing it over a very long time, right? So the only way in which your state can change in a finite way in your long infinite time limit is for psi dot to be 0.
But this is the
backwards. That's kind of
Just let me make a suggestion.
Next door.
You should go on, but there are subsequent terms in the adiabatic expansion which are well known and worked out. We can work this next term out in this model, and I'm sure we'll find that there's a change in the state.
That's exactly right. So you keep the next term which won't contribute to the derivative, it'll be like a delta t squared term. But because you're taking so long, that will cancel out.
Yeah, for a very long time, probably that.
Yeah.
So there's an extra contribution. So there's certainly a contribution to the phase that depends on e to the I energy times.
And the contribution to the change of the state. The state is changing. Suppose you wrote that as an infinitesimal, over a small time rather than as a derivative. Delta psi is equal to, you'll get your first term plus something else, and that something else will be of a kind that over an infinitely long time will integrate to a constant.
I mean, there
To
are
a finite thing, something independent of time.
That's what we got.
the way you wrote it, you got 0, right? Oh, we can know.
But the Berry phase is the thing that is the constant phase.
No, Shiraz, the point that you're worried about, that the instantaneous eigenstate is certainly changing direction as a vector, that's consistent with the statement that n dot is not being set to 0. N dot is the point you're
If psi dot is being set to 0, then the state is being, literally speaking, the point is this, that you see, the derivation would say that the change in psi is psi dot integrated over time.
Yes.
And you're saying, my contradiction was that if I take psi dot to 0 and I integrate over any finite amount of time, I get a 0 change in state. But I think the fallacy with my contradiction is that you're not integrating over a finite amount of time, you're integrating over an infinite amount of time. So it's 0 times infinity which will give you your constant. That's what I'm saying is going to be the resolution to my pattern.
Okay.
Yeah.
That's one way to say it.
Yeah.
Or
There's something, there's another issue here. This is something related to n,
That's right.
plus something proportional to n n dot. But these are not parallel vectors.
Exactly.
And so setting this to 0 can't be true in a Hilbert space because
That's the point.
these are not the same.
Yeah.
Same vectors.
So in some sense, maybe you're not just setting it to 0, you're just setting the overlap of this with psi to 0.
Exactly. I mean,
Dot is
we took the overlap with n, that can be 0. We're not taking the overlap.
Yeah, so the original equation may not have been
So that's
exactly right. Yeah.
That's the
Yeah.
better
I'm not sure. Yeah.
In fact, that's
In fact, n dot, n is always the normalized
That will be
eigenstate. N
just
dot is perpendicular.
Exactly. Yes.
so always perpendicular.
That's
Oh yeah, that gives you what?
That's the point.
Yeah, this will give you the u dot, u star u dot equal to.
And the bit that's not perpendicular to n is precisely the bit that's not captured within the A diagram. So there's two pieces here. There's the bit that's parallel to n.
The bit that's
So
perpendicular.
is what we wanted, right? We took the overlap with n to get our result. And then there's the bit that's orthogonal to n, which is really the bit that's perpendicular to parallel to n. And they can't both be.
you did get a contribution from the overlap and even from that second term. You just derived it.
Yes.
But there's extra components, right? Because that's your point. Yeah, and those are the ones you didn't keep track of.
They're the ones I didn't.
And I think they are the ones which will contribute to the higher orders. I think the corrections in the area. That's exactly right.
Sorry, Kedar, n dot is not.
No, it's
perpendicular
not.
to n.
Yeah. It cannot.
Yeah.
So it's not, but it must have a normalized vector.
No, so if you do this,
Right.
Right, exactly.
Right, exactly. Okay.
you just include.
That's all it means.
So I think that's exactly, you're absolutely right. That's exactly how you get the corrections to the area balance.
Exactly. So it was a little too strict. It's not this. It's this.
And we have to justify that. Okay, yeah.
I'll try and fix this up. Okay, so we have this simple example of a two-state system.
Let me ask. In the end, you've got this connection, which is a connection on the space of parameters of your Hamilton.
Exactly.
You had some interpretation of it as being the phase that you get in a time-to-time process. But when you actually use it, will you use that interpretation or you'll just use that connection?
No, well, we'll use it in many ways.
Okay.
And there will be some in which we use the time effect. We'll compute the fractional statistics of anyons and fractional Hall effect inputs, and then we're really thinking of a time process. Okay, by the way, if you haven't done this calculation, it's well worth doing. It's very informative. So what do we want to do? We want to compute the Berry connection over the space of parameters where the parameters are themselves the magnetic field. So the way you do it is you write B in polar coordinates. Which means you can then write the Hamiltonian in polar coordinates. Which means you can then write the ground state in terms of the polar coordinates of the magnetic field. is a normalized ground state. Similar for the excited state. It's important you deal with the normalized ground states when you do this. This ground state should only hold in some part of the magnetic field regime. It either breaks down near the North Pole or near the South Pole. So let's see if we can see this. The North Pole should be theta equals 0. Theta equals 0 and theta equals pi. Why does it go bad? Oh, it probably goes bad than this when theta is equal to 0.
So it's a Dirac thing, right? When you go very close to the North Pole, go around it, you get arbitrarily large phases because of the
theta equals 0.
Yeah. So this should hold only on one patch. You can write down a different ground state on the other patch. And it's that kind of topology that's important. You're trying to patch the ground states together that work.
You're just saying the phase becomes meaningless when theta is 0. It multiplies the number of dots.
I see. But that's true also at theta equals pi.
Yeah, that's why
theta by
Okay.
Yeah, so then it's theta equals 0 because then the phase doesn't
It's a problem at theta equals pi.
Good. Sorry, that's exactly the point, of course. These are the things that I called n of lambda before. So they're the reference states that have a specific phase. But as Shiraz pointed out, the phase breaks down when theta is equal to 0. So it doesn't have a specific phase. 0, we need a different set of states that cover that part of it. Okay, so we can compute the very phase. And you see something quite lovely. The field strength.
Sorry, David.
Yes.
What is wrong at theta equal to 0? It gives me a well-defined vector, right?
Doesn't have a well-defined phase. These were the things that had
0
specific
minus 1.
phase.
It's a
It's
vector.
like the bottom component as well defined.
It's just
There's
0.
no problem. I think the problem's at pi.
Oh, so what happens at pi? It's
Because you see, at pi, the sine theta by 2 is 1, and then what phi are you going to assign to the south pole? That's the problem.
That's
It's the south pole, that's
good.
not the north. This is just the usual.
good. So phi should be breaking down.
Yeah.
Good.
So this is in the upper hemisphere. Yes.
So if you compute the field strength, it's fine. So this is just computing the very phase and then taking the field strength of it. But it looks a bit more familiar if we go back to Cartesian coordinates. In Cartesian coordinates, the field strength is minus bk over 2 modulus of b cubed. Okay, so this is a very famous field strength. This is a Dirac monopole. But it's a Dirac monopole. It's a bit confusing. The usual place you think of a Dirac monopole is as a field strength in a magnetic field, living in another. But this is not that. This is a monopole over the space of magnetic fields. So it's something a little more subtle. It's a more abstract monopole, but it's a Dirac monopole. You can see that it has the usual radial charge of this sort of buried magnetic field, buried curvature coming out of it. It's got a singularity at the origin, but the singularity at the origin you can trace back in the quantum mechanics to the bit where the levels did cross. So there's something quite nice about this whole story. When you do this path in parameter space, you have to avoid the level crossing for the adiabatic theorem. But it's precisely that level crossing that's governing the physics of the path you're taking, avoiding the level crossing. So it's from the point where the levels cross that you get these sort of fluxes of buried curvature emerging, which are what you're picking up when you're moving further. Yes.
What was the right hand side there? BK over Z?
BK, no, that's a 2.
I was wondering what. Thank you. And there's a denominator B cubed?
B cubed, so it goes as 1 over B squared.
So the singularity you mentioned is therefore at B equal to 0,
The
right?
singularity is at B equals 0. And it's just where the two states have the same.
Right.
Okay, but it's a direct monopole in the space of magnetic fields.
So the fact that you can't be at B equal to 0 means the space of parameters, the topology is not just full space, it's
It's really R cubed minus that point, which is what gives you the topology.
and that
of
gives
S2.
you the non-trivial topology.
And suppose we can read out S in a different representation of SU class.
You have a bunch of, you have 3 states.
Yes,
You look at one of them, they all become degenerate, and it must be a magnetic monopole, but probably of higher charge. That would be my guess. It must be a magnetic.
No, well, actually, couldn't I just say that idiomatically I'm just going to rotate the spin coherent state around, and for spin S, it's either going to be pi or 0 depending on whether S is half integer or
Is that?
I would say so. So if it was spin 1, I would say there's no phase in this calculation. If it's spin 3 hours, it's again pi. Just write down this coherent state representation. And what you're really, the ground state is the coherent state along the, and as you change B, you're doing a rotation. And we know that 2 pi rotations for half odd integers give pi.
And another way of saying it is let's take spin 1. We've got 3 states.
Yes.
The sum of all of them has to be 0. So here, if I did the upper state, I'd get a direct monopole.
No, I'm just saying 2 pi rotations of spin 1 objects don't have a phase. Whereas 2 pi rotations of half integer, half odd integer.
It's a different spin. Is it the same spin? It's not. It's not spin statistics.
No, not spin statistics. I'm simply saying when you represent rotations, the rotation operator for in the Hilbert space of spin S variables. And so when S is half odd integer versus when S is integer. Like one of them has a pi, one of them doesn't. That's all. Because you think of spin 1 as a symmetric product of 2 spin halves. There are 2 pi's. They give you 0.
I guess what.
I don't know. That's a bit too quick for me.
Okay, maybe I'm wrong. You should check this. I would say there's no monopole in the spin 1 case.
But in the spin 1 case, they definitely have to add to 0. So it can't be that the spin up could be.
Yeah, no, I'm only making a statement about the total phase accumulated by this process. I'm not saying whether that's somehow coming from something that's non-zero is cancelled.
And the total phase being pi is a little odd here, right? The total phase being pi is when you choose to go around the equator in magnetic field space.
Yeah.
In general, the phase is not pi. If I move around in some region, it's just you pick up the flux emitted by this monopole, and that's the phase.
In this case, it's pi because you went around and did a 2 pi rotation. Right?
I didn't do anything yet. I just computed the very connection. Now I can choose how I change my magnetic field.
Okay.
So
I'm
if I
saying
change the
you went-
magnetic field
yeah.
like this, I just get the solid angle of
Right.
the magnetic
Right.
field.
No, that's right. So I'm just saying if you go around along the equator,
Then I
you
get
get
pi.
pi or 0.
Right. But suppose you went around not around the equator, some smaller patch, then you get this pi. So it's not just the magnetic just hands. Right? Because spin 1 can be built out of 2 spin halves.
2 spin up, just symmetric.
Yeah.
Right.
So having a charge 2 is the same as what you said. You get a 2
Yeah.
pi
Yeah.
if you go around.
Yeah.
That's
Yeah.
So the magnetic field is just spin.
But I'm not. But you've got 3 states, so there's a very connection for each of them, and it could be that it's minus 2, 0, and 2.
But let's say the lowest spin half, the highest weight state,
Yeah.
because that's
the
exactly
one
product
that
of 2 spin
yeah.
half highest.
I mean, I'm taking the analog of your ground state.
Right.
Which is
Yeah, so I suspect
maximally
it's-
polarized
It's
along.
charge 2 monopole.
Charge 2 monopole, maybe charge minus 2 and 0.
I suspect so, but I.
Yeah.
Okay.
Yeah.
I'm not sure.
So maybe just JZ component of the spin that determines the charge.
Mm.
It would be an easy calculation to do if any students are keen. That's all I wanted to say about the Berry phase. I'll add a few more comments. One nice generalization arises if you have degenerate ground states. So if you have degenerate ground states and you keep the degeneracy for all values of the parameters, the adiabatic theorem says that now as you change the parameters, you cling only to that energy subspace. It doesn't tell you that you cling to the same particular state that you started. Which means that now when you come back, you don't just get a phase, you get a unitary operator that rotates you from within that energy subspace. So the Berry connection becomes a non-abelian gauge connection. The choice of, the arbitrary choice of a basis for that subspace and changing that choice turns into non-abelian gauge transformations. And you play the same game, but now using the kind of things we see in Mill's theory rather than the kind of things we see in Maxwell.
And you alluded to some result which is the sum of Berry phases is 0. Where does that come from?
What's really going on here is you're looking at how the particular subspace of interest is winding within the total Hilbert space. That's kind of the physics. But the total Hilbert space itself is not changing. I think that's the intention.
Oh. So you're saying in this example, if I took the high energies, there are two states, not the ground state but the other one, I'll get the
minus. By the way, it's worth stressing this obeys Dirac quantization, but it has to obey Dirac quantization for all the reasons that Dirac are actual. I can advertise a paper I'm very proud of from about 5 years ago that no one's ever read, but with Julian Sonner we cooked up a very simple quantum mechanics system that gives the BPS Toft-Polyakov monopole as the Berry phase. So it's a simple generalization of this. It's a particle with spin up and spin down moving on a sphere with a potential. And it's cooked up so that if the particle sits at the north pole, it's got two ground states, north and south pole, but in the north pole the ground state is when the particle is spin up. South pole the particle is spin down. There's two ground states for all values of the potential or the magnetic field. And when you compute the non-abelian Berry connection, it's exactly this BPS. So you can really start to play some nice games.
I see. So just to understand, it's a non-abelian.
It's a non-abelian Berry phase because there's two ground states and all that. And it's quite nice because now you don't have a singularity. That's kind of the beauty of the top polygon. There's no level of crossing, you still get this.
So you should get a U2, or does it?
It's U2, but actually the U1 is trivial in this case, so it's just SU2. Okay, other questions? All right. So there's a couple more things that I want to talk about that are related to Berry phase. And again, I'm just going to cover them because they'll be very important in the follows. So they're both to do with particles moving in the background of magnetic fields.
Can I just ask one small question about the example you did? Which is, here you considered adiabatic sparks where the magnitude of V was fixed, right?
No, not necessarily.
It's just so it would still be this monopole even if the magnitude of V was varying as you allowed it.
Yeah. So when you go around, if you the Berry phase is the flux that goes through that loop that you've drawn in V space. And if that loop comes in and out again, it doesn't matter, it's just the solid angle that it makes.
So somehow it doesn't matter that it comes in.
As long as you don't go to the origin. That's the only assumption.
Yeah, it's just as if you had stayed.
No, that's because changing the magnitude of B doesn't change.
So you're saying if I had higher spin than larger spin, what's going to change? It's going to be the same magnetic monopole's magnetic field, but the particle that's moving around it will have higher magnetic charge.
I don't think there's any invariant way to distinguish between the monopole
Between
having
the
charge
charge.
and the charge of because it's not really a particle, right? It's just the motion of the parameters.
Right. So I guess it's just the product.
So what happens if there are more than one degeneracy parameters, right?
Typically, each of them gives rise to a Dirac monopole. If it's a level crossing where you have two states on the side, you just get a bunch of monopoles. Some with charge plus, some with charge minus. Okay. Other questions? Yeah. All right, so let's just do, again, some simple quantum mechanics. We're going to take a solenoid with magnetic field B and flux and then outside the solenoid, of course, B is equal to 0. Solenoids. And then we're going to put a particle moving around this solenoid that's constrained to lie on a ring. So the ring has radius r, and there's a quantum mechanical particle which is just going to be moving on this ring. So it's fixed to move on this ring. So consider a solenoid. Particle moving on the ring. Radius r. And looking back in your basic electromagnetism notes, the gauge field associated to a solenoid outside the solenoid is phi over 2 pi r. There's two phis here, they have nothing to do with each other. Capital phi is the flux, little phi is the angular variable around the cell. Okay, so this is the gauge potential that gives rise to that arises from the solenoid outside the solenoid. Okay, so what's the Hamiltonian? So the Hamiltonian is very straightforward, it's just momentum squared plus the gauge directions. And the eigenstates are very easy, they're just the same eigenstates that we would usually use for a particle in a circle. R is not dynamical, remember. R is just the fixed radius. Phi is the dynamical degree of freedom. And if we want these to be single valued, then n should be valued in Z. And if I plug this in, it's easy to get the energy. We have a tiny bit of algebra. So there's some factor up front, and then it's n plus phi divided by phi 0, where phi 0 is the quantum of flux, which is one of these three numbers that's just going to arise over and over again, and is written on the right-hand side. Okay, so what's the lesson to learn from this? It's very simple, a very simple system, but it has something that's going to be very important when we come to discuss the integer quantum Hall effect. So firstly, remember that there's a state for every integer n, which means the spectrum, this is the spectrum, and I should just look at all possible integers n to give me the full spectrum. It means that the spectrum is exactly the same whenever phi is an integer value of phi 0. If phi is an integer value of phi 0, this is an integer, and I just absorb it into the integer n here. Or in general, the spectrum depends only on the fractional part of phi over phi. So the spectrum can change over phi. Integer multiple of phi 0, and we can also think about how the spectrum changes as phi 0 increases. So this is E, this is phi, and this is the n equals 0 state, it's going to go to 0. And then the n equals 1 state looks exactly the same as this. And the n equals 2 state like this. Okay, so if phi is equal to 0, when we just look at the standard spectrum, the spectrum is here, 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 and so on, but at any phi, just read on to see what the spectrum is. So the nice thing is the following. Suppose we start with phi equals 0, and then we very slowly increase phi until it becomes this unit of flux. So by the time phi increases from 0 to phi 0, the spectrum is completely the same. Okay, so the spectrum here is completely the same as the spectrum here. But if you look at any individual state, that state has shifted. So suppose we put ourselves in the ground state when phi is equal to 0, and then we slowly increase phi from 0 to phi 0. The ground state changes to here by the adiabatic theorem, and by the time you got to phi 0, you're no longer in the ground state. I guess the adiabatic theorem isn't really allowed.
Yeah.
This level of crossing. But yeah, okay. Nonetheless, you can sort of see that the states are changing. Okay? You can't do this physically because of this level of crossing. I can't place myself here and then move up. But nonetheless, you can see that this state shifts to the first excited state, and all the states change. So start with phi 0. Start with phi equals 0. Increase the constant flux. The spectrum is the same. But state n is shifted to n plus 1. And so this is an example of something that's called spectral flow. You change a parameter and the spectrum continuously morphs back into the original spectrum, but with all the states shifted. So this is an example. Okay, and we'll see this arising in the integer quantum Hall effect. Any questions about this? And one last thing I want to tell you about, which arises in the same system, which is very famous, and it's an example of Berry phase, but again, an example that was discovered long before Berry realized this was a generic phenomenon, and it's called the Aronoff-Bohm effect. And to see it, you can think back to this solenoid. So this is V, or let me call it in terms of flux phi. And now, rather than allowing the particle to move around this ring, let's confine it to a box. So there's some wave function living in this box. We'll put the box at some position x. And it's going to be a capital X. And now the Hamiltonian is 1 over 2m. This is the gauge potential that the particle feels. This is the potential which firstly is going to trap the particle in the box. It could be doing anything else to the particle. It can just be some general physics that's happening in this box. So what do? You solve the energy inequalities. And now what we're going to do is think about moving this box very slowly.
Actually, it's worth moving the chair a little. Thank you.
So we move the box very slowly around the solenoid, not going near the solenoid. So what's happening? The variable is now x. The parameter is now x. So now we get some Berry phase. In principle, we get a Berry phase where it's a Berry phase over position space itself. Position space labeled by this position of the box x. So we can move this box around, and you can ask what is the Berry phase that arises from this Hamiltonian, with this being the parameter. So move the box. So x is the velocity, is the parameter. So you can simply check that the very connection remember, is a curly A. And in this case, it's very nice. The very connection is precisely equal to the electromagnetic connection. So the electromagnetic connection is sitting there in the Hamiltonian. And for any given situation, it's not playing any role. You can always just gauge it away for any given situation. And it's only if this box starts to explore the whole space, and in particular comes around, that you can't gauge it away. If the box moves around, all the states of the Hamiltonian will come back to themselves up to a phase. That phase is phase. So taking a particle around the flux tube, gives rise to a Berry phase, which in this context is called the Yaharova-Bohm phase.
Isn't there an extra somehow momentum? dH over dx will give p times a, isn't it?
H?
I guess I take it in the state. It doesn't matter which state I take it in.
I didn't understand the question, but it doesn't matter which state you take.
Yeah, the Berry connection, I get to really verify this, I have to look at an energy eigenstate and then
look at energy eigenstate,
and then look at d by dx of that.
It would be true of any energy eigenstate.
This A of x there, that x is small x, right?
Good. So what's happening? I'm assuming you're writing this Hamiltonian.
It's a very small box.
It's a very small box relative to the size of this distance. So yeah, this distance here. So D is much smaller than 1. So that I can approximate the gauge connection just as a single value within a given system.
Actually, what kind of calculation did you do to verify this?
Explicit.
Just roughly, how is the phase going to come into the? How is this affected? I mean, the eigenstate is going to be basically the position eigenstate.
Yes.
The ground state, and then why can't I choose that phase totally out of the?
You can gauge it away unless you come around.
Yeah, but how? I'll just try.
Let's see.
So as far as any given Hamiltonian is concerned, this is a constant vector potential, A of x. When x is fixed, it's just a constant. It doesn't depend on little x, right? The vector potential doesn't depend on little x. So it's just a constant.
Yeah, why? Because we have a small box.
I was also confused about this. So you take some state and then you vary d by d lambda, and you should get a dependence, is it?
Shall I go through what I...
Oh, you should.
I haven't.
Okay. let me just hang on that. Okay, so we'll take the ground state. Sorry. Okay. This just sits here. Let's pick a gauge so this matches.
Okay.
Such that A at some initial point x0 is equal to 0. Now we'll take the ground state. Which is now localized in some small region around x0 to be this. So now move the box. So the new ground state for this Hamiltonian you can show is e to the minus I e over h bar integral from x equals 0 to x equal ux a of x to psi of x minus x. Okay, so the claim is that if that for any value of a that I had in that Hamiltonian, if I change the value of a, I can always get my new ground state just by gauge rotation, just by changing the. So that's something you can check. You plug this into the Hamiltonian. It's the derivative gets this and brings down the a to cancel.
Yeah.
Cancel. But this is exactly the kind of thing that we want for variables. So.
What is the parameter in your problem?
Capital X, position of the box.
Sorry, so this is the new eigenstate when you change what?
I've changed X, so I chose some gauge where this was 0 at some initial. Now I change the position of the box.
Okay.
Capital X.
But why can't I choose the new eigenstate to be an arbitrary phase?
Why doesn't it be a bad
Let's see. So the Hamiltonian has a of x that sits in. If you give me one Hamilton, the eigenstate of a Hamiltonian with a of x equals 0, I can give you back an eigenstate of a new Hamiltonian, which just differs by this.
But this is just a phase, right? I mean,
But Shiraj, you could have asked this question about any very phase example.
It's when you come back.
You're inheriting the phase from the slowness of the dynamic. You're following the real dynamics in the arbitrarily slow element, right?
Nothing invariant happens until I come back to where I started. That's
yeah.
it's only if I move all the way around and come back, this picks up some phase that I can't get rid of.
I guess the point is that very connection is, that's obviously not a gauge invariant quantity, but the integral over a path, this is the flux of, that is a gauge invariant quantity. And yeah, you can't, if it's finite, you can't gauge it away.
But I just want to see that the change when I move x to x plus delta x, that there is some, that the very connection as you defined it, this d by d lambda, that had to be non-zero. So I'm not saying that you can't choose the phase to be equal at the 2 points.
You
can.
But the convention,
and that will still give you a non-zero over the.
you cannot consistently do it if you are coming back.
Where do I know that? Bit by bit. Yeah. So I'll ask you.
But here, Shiraz, it's literally a gauge transformation.
It's
Effectively going to a new location is literally doing the gauge transformation on the old function. So it's just that bit by bit you could always ungauge it. But
what's not totally clear to me is how the calculation. I'll
keep track of it.
Yeah.
the Aronoff moment. If you move a particle around a flux tube, it comes back to itself up to this space. And it's something which is detectable. As far as I'm aware, detected. You take a particle, you make it go in, you split it so it goes through two slits at the same time, but between them you suddenly put this solenoid that neither particle hits. When they come back to themselves to interfere, they come back with a shift in phase, which is precise. By the way, a kind of scattering experiment, the way this is usually phrased in.
Yeah. No, it's certainly true that if you compare two parts in a path integral, this one and this one differ by phase. That is, I was just trying to put it into the language. I'm just confused. So certainly it leads to non-trivial scattering. I don't dispute that.
Yeah, this is an attempt to try and relate it to Berry phase, because otherwise it sounds a little bit different if you're doing scattering. But I think it is the Berry phase for this particle.
So I think the only thing that you can define in a gauge invariant way is when you come back. Otherwise, there's no meaning to the phase acquired because you can always gauge it away. So the only meaningful thing you can talk about in this is when you do a trajectory which comes back.
Maybe to put it in the language of this, the ground state of the Hamiltonian P minus A square plus V will be related to the ground state of the Hamiltonian P square plus V by the extra phase e to the integral of A.
Right.
So from that we deduce that the Berry connection is the physical gauge.
But in doing so, you are making the electron, which was originally single value, into quasi-periodic thing, and the amount of quasi-periodicity is...
no quasi-periodicity, because I put it in the box. That's why I precisely did the box.
This guy will, in general, not be periodic, right? It's very function.
Because it picks up this phase, but this wave function was only ever localized in some small region. So the wave function in this particular problem never spread around, so it never had an issue.
Okay.
But it being non-single line. Yeah, in fact, we saw before that we allow it to spread around. Wave functions don't depend on that. The wave function is always just e to the n times 5 because I wanted them to be single valued, but the energies of those wave functions. Okay, that's the end of my introduction to basic quantum mechanics. Any questions? What should we do? Should we postpone it?
So is Berry phase always dependent on the path? If I reverse the way I'm changing, the time reverse manner, do I acquire a negative Berry phase? I mean,
yes, you get exactly the opposite Berry phase if you took exactly the opposite. Which is why if you just have one parameter, you never get any Berry phase. Because you've got to go there and then come back along the same path. It's only when you have at least two parameters that you can start to do closed loops.
My suggestion is that if people have the energy, we can continue to 150.
But I mean,
Does
it help in terms of break? If this is an actual break point.
So we'll move on to the integer quantum Hall. Let's see. But you know, any break is an actual break. All right. Okay, so section 2. It's the integer quantum Hall effect. We're going to do a bunch of different things in this. To begin with, I'm going to try and I'm going to be a little bit heuristic. There's not going to be any sophisticated mathematics. And then towards the end, I'll try and relate the integer quantum Hall effect to some beautiful things in geometry, things like Chern classes and what's called the TKNN formula. So that's kind of the goal, is to prove this TKNN formula. But to begin with, what I want to do is sort of just give you a sense about why the integer quantum Hall effect arises and why it's much more subtle than you might think. Okay, so the problem of the integer quantum Hall effect can be understood purely with non-interactive electrons. This lecture or the next lecture. So the essence is very straightforward. So we saw integers arising in two places in the calculations we've done. We saw integers in two places. One of them was the calculation. It was the experimental fact that you look at the Hall resistivity versus the magnetic field. This was the classical expectation, and what was seen was a sequence of steps, and these steps were labeled by integers. U equals 1, U equals 2. Right, I think they go down all the way to about U equals 10. And the other integers was a simple calculation we did of just an electron moving in a magnetic field, and we saw that they form Landau levels. The Landau levels have a huge density of states. There's an enormous degeneracy of each Landau level, and yeah, 3 is the next one. Good. So the very obvious guess is that these integers here have something to do with these integers. And this very obvious guess is, of course, correct. So let's just see, just from the calculations we did in the last lecture, how that works. So on a plateau, so I mentioned that experimentally on a plateau, this is the value that the Hall resistivity takes. And we're going to see that this corresponds to new filled Landau levels. And you can do this calculation in kind of increasing ways of sophistication. Let me do the simplest calculation here, which is kind of half classical and half quantum. Completely classical, actually. Let's see. So the classical Drudel formula that we derived in the last lecture told us that rho xy was b over NE, where n is the density of electrons. Remember, the classical Drudel formula is valid here because although it goes up in steps, it does go up in line with the classical expectation. So the centers of the plateaus are basically where the classical Drudel formula holds. And so just comparing this with this result, we can extract what the density of electrons must be. The density of electrons is B over phi 0, so it's nu. Where phi 0 is this quantity flux, which is up there. But this is exactly the density of electrons that's required to fill new Landau levels.
The width of the plateau, is it related to this K degeneracy?
No. We're going to see what it's related to. It's related to the amount of disorder. It's quite complicated. And what's more, if you fill exactly new Landau levels, so you filled all of these, you filled all of these, but you haven't filled any of these, then this is what we would call in condensed matter physics an insulator. Because if you want to add one more electron, or if you want to excite one of these electrons into a new state, it's going to cost you some energy. And the energy is going to be h bar times omega b, where omega b is the cyclotron frequency. So when you feel the Landau levels, the next state, the next available state, costs energy h bar omega b. And so as long as you're at small temperatures, so you don't have enough thermal energy to just excite this system, you're stuck here, and we have an insulator. It's an insulator in the language of Drude physics. The scattering time goes to infinity, and from our Drude calculations in the last lecture, we saw that conductivity, the longitudinal conductivity is 0 in an insulator, and perhaps slightly more surprisingly, the resistivity is also 0 in an insulator, which sounds unusual, but as we saw in the last lecture, because rho xy is. Okay. And remember that if you were to plot rho xy here, you also found that it was 0 when we were on. Alright, so this was a very simple calculation. We can do calculations of increasing sophistication. In the notes, there's just a quick page calculation which redoes this, all using quantum mechanics language rather than relying on the Drude picture. It's a very simple calculation, and I won't repeat here. And you can keep going in sophistication. You can start invoking Kubo formula, and start doing it in more and more complicated ways. You just find this result holds. If new Landau levels are filled, where new is an integer, then rho xy takes this value, and rho xx is. Okay. That sounds as if it's an explanation for the quantum Hall effect. But in fact, it doesn't explain anything at all. It certainly doesn't explain why you get these plateaus. So let me tell you why this is. In Cambridge, we don't teach. I'm in the maths department. We don't teach any physics. But in the physics department, they do teach the quantum Hall effect, and they get this far, and then they pretend that this is an explanation. So let me explain why this. And I think most undergraduate courses do this. So let me explain why this is not an explanation. Suppose you fix the number of electrons in your system, okay? And you fix them so that exactly some number of Landau levels is filled, and so that the Hall conductivity is precisely what you would expect on plasma. And now you increase the magnetic field just a little. So what happens? You increase the magnetic field, the number of states, the degeneracy of each Landau level increases, because the degeneracy of each Landau level is proportional to B. So suddenly there's many more available states in each of these. So some of these electrons tumble down into the first Landau level, and as soon as you increase the magnetic field, you no longer have a filled Landau level. So suddenly none of these calculations hold. So you would expect that in any system, as soon as you increase the magnetic field away from this very specific value here, that you deviate away from the Hall resistance. And yet very clearly that's not happening in this system. So our goal is to try and understand why we're seeing these plateaus at all in quantum Hall physics. It's clear it has nothing to do with filled Landau levels, but it's clear that that alone is not sufficient to explain. Questions? So that's what we're going to do next. By the way, before we go on, just a quick aside. In the notes, I had a few pages about edge modes in the quantum Hall effect. And I was thinking of doing it here, but I think, given time, I'll skip it. So you can understand very easily that in the integer quantum Hall effect, there are edge modes. And the edge modes have the nice property that they're chiral, meaning that if this is your quantum Hall sample, they go this way around the sample. And it turns out that this is really important. It's related to all sorts of things to do with conformal field theories, on the boundary. And if we have time, we'll discuss this in great detail at the end of these lectures. So I'll skip it now, but there is a very, very simple way just to see edge modes and the integer effect, which is described in the notes if you're interested. Okay, but let's focus on this question about why the quantum Hall state exists at all. So the robustness of the Hall state. So if new Landau levels are filled, then rho xy is takes this quantized value. The question is, why do new Landau levels, they're going to abbreviate Landau levels as L, remain filled as V varies? Which must be the case experimentally because we see these results. In other words, why do we see that?
Sorry, could you say that argument once again? What the contradiction is, why it doesn't explain as a way.
Good. So let's fix B, and with fixed B, there's a particular degeneracy of Landau. Let's throw in exactly the right amount of electrons, which fills up the first two Landau levels. Okay? Then we know experimentally that the physics that we observe there is we predict theoretically that we observe exactly the physics that is seen. Okay? Now let's keep the number of electrons fixed, because that's what you do in an experiment, and vary B. So what happens? As you vary B, each of these Landau levels gets a greatly increased degeneracy. So each one can house many more electrons. So on energetic grounds, the electrons that were up here will tumble down to here. And now you will no longer have a partially filled Landau. So none of these arguments that we used before will go through. In particular, it's not going to be an insulator. You would expect that, as you apply an electric field, there's extra states that these particles can move into. It's going to respond much more like a conductor. And yet, this doesn't happen.
Okay. And you see, that doesn't happen from the fact that those fields are zero.
This.
That was needed for that there was no that was an insulator was needed to get.
Yeah, the insulator was needed for this. To get this Hall plateau, you needed the density to be exactly such that new Landau level. And that's not true either. Very deep. New Landau levels are filled precisely at these points.
You see, the fact that it's not just a straight line.
Right, exactly. Actually, quantum mechanics is predicting classical mechanics.
So, genuine free quantum mechanics predicts straight line.
Depends what you mean by free quantum mechanics. You don't need interactions between electrons, but if you just have electrons and nothing else, it predicts straight line.
Yes.
Yeah.
And for various, I suspect that's true even with arbitrarily strong interactions between electrons. These are to do with disorder.
But at least for the genuine free problem, you're saying there's nothing special about field Landau. No, as far as rho.
There is, but it's
So it's an insulator.
No, before as far as rho xy goes. It just doesn't care whether it's full filled or not.
No, but wait. I thought in the free electron picture, when you hit the Landau level, then rho xx will plummet exactly at that one place.
Yes.
And then come back up again.
Yes.
Right.
Exactly.
So the question you're trying to answer is why that plummeting is not just at one place of rho xs, but is a spread out region.
Both. Why rho xx is zero
Yeah.
for such a long time, and why this is
fixed intervals.
I mean, there is still something special about hitting the Landau level, but it's restricted to that one place.
But yeah, nothing special that you would see experimentally.
Not in rho xy, but in rho xx.
Yeah, rho xx you would see a
you will
different.
keep seeing dips.
I know nothing about experiments, but if it's really one place, would you see anything?
Yeah.
I don't.
Down.
So the answer is has a wonderful irony to it. So the answer is disorder. And it's quite lovely. I said in the last lectures the quantum Hall effect is one of the most precisely measured things in all of science. These integers are measured to something like 8 decimal places. So you get this astonishingly good quantization. And yet the reason you get this astonishingly good quantization turns out to be because of dirty, crappy stuff that's in the system. So it's really quite cute the way this works out.
So, one more question. So just about rho XX. At exactly filled points, I understand that there's no current. So that's good. So now if it's just a little bit unfilled,
yes.
What would just free ordinary quantum mechanics say?
I don't think you come up with
it. It would conduct with the magnitude of the conductivity go to zero smoothly. It's basically because
there's very few carriers in the next half filled level. Right? So there's some number of filled levels, and then you add a few more particles.
I think the answer would be not trivial because it's a single delta function with a macroscopic degeneracy.
Right.
It doesn't have a density of states that you are talking about.
Right.
So I'm not sure it will be small change. I don't know.
But if you add an electric field, the Landau levels no longer become degenerate. Right? So in the presence of an electric field, they tilt slightly.
Right.
And would all fall down to fill these ones, and there would just be a persistent.
There would be a current.
Yeah.
There would be a current. Would that current go to zero?
Are you asking is that limit singular or
yeah?
No, the current must go to zero one by one as the electrons move from here. It must increase smoothly from zero.
So could you make a cartoon sketch of what you would get for rho XX in the free theory? In the non-dirty theory.
No, in the non-dirty.
Yeah.
This is what's seen. This is
the dotted line is what you get for rho XY in the non-dirty theory. That's right.
So this should be zero. It should be zero there.
So those are the filled line levels.
Yeah, and presumably the current increases. Seems likely it increases this way and this way, depending if you have holes or. And I don't know if it diverges. I don't know if it diverges or if it's something similar.
Oh, but in the non-dirty theory, since there's no scattering, it's always zero infinity.
Yeah. It's always zero.
Okay, so you need some dirt.
I'm not sure that's true. So this is what the Landau levels look like with an electric field. They tilt slightly. So there's no longer a degeneracy.
It's not degenerate.
So I think.
Wait, what are the classic? Sorry, I asked you this before. But what are the classical parts of an cross electric and magnetic field?
They do this.
They move in the direction of the big.
They move in the direction of E. Yeah, they drift in the direction of E. They drift in the direction perpendicular to E. Yes.
So that classically, there's no current, even without impurities.
Yeah.
So does that mean it should always zero?
What happens here?
So without impurity, of course, if you've got an impurity, it starts moving a bit and then gets knocked and starts moving again. So there's current. The knocking makes the current.
Knocking is what you
stops you from going all the time.
circular orbit.
Yeah. But without impurity, maybe there's just never a current.
Yeah, you need to get a scattering to get out of the circular orbit. They go to the next circular orbit and then again get scattered. That's how you typically conduct when you have impurity. And one classical thing.
All of these states carry a current, but they carry a current in the y direction, not in the.
Yeah.
So they extend. So classically, it would just be zero. I mean, in the non-dirty theory, it would just be zero.
So if I go to the better calculation. So you want to compute the current in a correct quantum calculation. You sum over, assuming they're all filled, you sum over all the Landau levels that are filled, and then the degeneracy. Where these are now the ground states at the Landau level, but in the presence of an electric field, which you can compute analytically is very straightforward. And this is, each of these are harmonic oscillators.
Yeah, this is zero.
And this is zero, well, not when you sum over everything, but I think it's zero term by term.
Yeah, well, except I'm worried whether it's zero about the center of mass of that, or center whatever the harmonic oscillator.
You're saying you get shifted.
These are shifted harmonic
But
oscillators.
they're shifted. They're
If you're working in random,
They're shifted, but
Well,
they're still harmonic oscillators which,
Yes.
which don't care about left and they're still symmetric between left and
del del x doesn't care about the shift. No?
Yeah.
It's a harmonic oscillator at x minus whatever x naught.
But I think this is zero for, not when you sum over all k, but term by term.
Term by term.
This matches.
It sounds right.
Yeah.
Because if it's a Gaussian e to the minus alpha x minus
It is a Gaussian, right, exactly.
Right, it should vanish.
Yeah, no, it's a Gaussian, and the only effect of the electric field is to cost you energy.
Energy, not
As you move, not to shift the wave functions themselves. They remain the same. So it's zero.
So what does the sum do? I mean, you're saying not when you sum over.
No, it's zero term by term, and the sum adds up lots of zeros.
That's all.
All right, so I think this is probably a good place to stop. In the next lecture, we'll understand, at least heuristically, why disorder is giving rise to these.